Here's a question that should keep you awake. Why would the US government track a comet with military precision for 20 years? The answer leaked on November 2nd, 2025, when classified files surfaced showing 3I Atlas with geometry no natural object should possess. Sharp boundaries, directed emissions, structural integrity at perihelion where thermal stress should have torn it apart. The images carried designations from CASSANDRA and ARGUS VIS, systems that officially don't exist but match the naming conventions of actual defense intelligence networks. NASA's public data shows a normal comet. The Cassandra leak shows something else. Something that either breaks physics or was never made by physics in the first place. Stay with me through this analysis, because we're going to forensically examine these files, compare them to verified sensor data, and explore exactly what it means if an interstellar visitor required 2 decades of classified military surveillance. Keep watching, because 3I Atlas is still out there, and telescopes continue tracking it as those leaked Cassandra images haunt the back of every astronomer's mind. Subscribe to follow this mystery, because the next observation could change everything we think we know. They told us it was just a comet. On November 2nd, 2025, that story started to fall apart. A set of classified images surfaced on public forums that morning, uploaded by an account that would be deleted within hours. The files carried headers that made seasoned defense analysts go quiet. Cassandra/Oracle 6, vertical bar, Argus VIS. Those aren't the labels you see on university telescope data. Those are the kind of designations that appear on military intelligence networks, on satellite reconnaissance systems, on things that governments don't talk about in press conferences. The images themselves showed something that shouldn't exist. 3I Atlas, the interstellar visitor that astronomers had been tracking since it entered our solar system, had just completed its closest approach to the Sun. Standard comet physics told us what should happen next. The object should fragment, should tear itself apart under the immense gravitational and thermal stress of passing within 24 million miles of a star's surface. Comets don't survive that kind of punishment with their structure intact. They become clouds of debris, streams of vaporized ice and dust, cosmic roadkill scattered across the inner solar system. But according to these leaked files, 3I Atlas did something different. The images purported to show an object with sharp geometric boundaries, a structured core that maintained its integrity through temperatures that would vaporize lead. Even stranger, the alleged sensor data showed plasma streams that didn't behave like normal cometary outgassing. These weren't the chaotic jets of vapor you'd expect from sublimating ice. According to the leak, these streams showed directional control, pulsed emissions, patterns that looked disturbingly like exhaust from a propulsion system. Now, here's where we need to pump the brakes for a moment. NASA's publicly released observations tell a completely different story. The Hubble Space Telescope tracked 3I Atlas through its solar approach. The James Webb Space Telescope turned its infrared eyes toward the object. MAVEN and the Mars Reconnaissance Orbiter captured images from their positions around the red planet. Earth-based telescopes from Chile to Hawaii pointed their instruments at this interstellar traveler. All of them showed something remarkably ordinary. They saw a comet with a typical coma, that fuzzy cloud of gas and dust that surrounds an active comet nucleus. They recorded a tail streaming away from the sun, exactly as radiation pressure and solar wind would produce. They detected outgassing signatures consistent with sublimation, the process where solid ice transforms directly into gas when exposed to the sun's heat. So we have 2 competing narratives. On one side, official scientific institutions with transparent methodologies and peer-reviewed data showing a comet behaving like a comet. On the other side, anonymous forum posts claiming classified military sensors captured something that breaks our understanding of celestial mechanics. The alternative science communities, the UFO researchers, the conspiracy theorists, they latched onto the Cassandra files immediately. Within 48 hours, the images had been shared tens of thousands of times. Across Reddit, Twitter, specialized forums dedicated to unexplained phenomena. Analysis threads sprawled across hundreds of comments as amateur sleuths tried to authenticate the metadata, enhance the images, decode the file headers. Some claimed they could see artificial structures in the enhanced versions. Others insisted the thermal signatures were all wrong for natural outgassing. A few pointed out inconsistencies that suggested the whole thing might be an elaborate hoax. But here's what makes this leak different from the usual grainy UFO footage or blurry photographs of lights in the sky. The technical language in those file headers shows knowledge of actual defense systems. Argus, for instance, isn't a made-up name. DARPA, the Defense Advanced Research Projects Agency, really did develop Argus-IS, a gigapixel video surveillance system designed for airborne platforms. It's real technology, documented in defense industry publications. Whether a space-based version exists, that's classified territory. Oracle, similarly, follows the naming conventions of military satellite programs. We know from declassified documents that the National Reconnaissance Office, America's spy satellite agency, uses project names drawn from mythology and prophecy. Oracle fits that pattern perfectly. And Cassandra, that name appeared in a 2005 planetary defense proposal. Scientists suggested a network of sensors to track potentially hazardous asteroids and comets, an early warning system for cosmic threats. The proposal never received public funding, or at least no public funding that shows up in NASA's budget reports. So these file headers demonstrate either insider knowledge of real defense programs, or someone did their homework before creating a very convincing fake. The question becomes, why would someone with access to actual classified systems risk prison to leak images of a comet? And if it's a hoax, why go to such elaborate lengths to make it believable? The story gets stranger when you consider the timing. 3I Atlas was discovered in early 2025, giving governments months to prepare observation campaigns. If classified sensors really were tracking it, they would have had plenty of time to position assets, to coordinate with allied space agencies, to establish whatever protocols exist for monitoring interstellar visitors. The fact that these alleged images surfaced immediately after perihelion, the point of closest solar approach, suggests either an intelligence leak timed for maximum impact, or a hoax designed to capitalize on public interest at the peak of 3I Atlas's visibility. But what if the files are genuine? What if somewhere in a secure facility, analysts really are studying high-definition imagery of an interstellar object that behaved in ways that shouldn't be possible? That's the question keeping astronomers up at night, even the ones who dismiss the leak as obvious disinformation. Because if there's even a chance, even a tiny possibility, that 3I Atlas isn't what we think it is, then we need to know. We need to see the actual data, run the real analysis, apply scientific rigor to extraordinary claims. The problem is, extraordinary claims require extraordinary evidence, and anonymous forum posts don't qualify as evidence in the scientific community. Which brings us to the next question. What are these Cassandra files really, and do they hold up under scrutiny? Let's decode what we're actually looking at. Those file headers that appeared in the leak, they're not random strings of characters. Each component carries specific meaning in military and intelligence nomenclature, and understanding them reveals either a legitimate classification system or a very sophisticated fabrication. Start with Argus-VIS. The interpretation circulating among analysts suggests this designates a visible spectrum high-resolution sensor, presumably space-based given the context. We know Argus-is exists as ground truth. That system, developed under DARPA funding in the early 2010s, consists of 368 smartphone sensors arranged into a single gigapixel camera. It can capture video of an entire medium-sized city at once with enough resolution to track individual pedestrians and vehicles in real time. The technology is documented, publicly acknowledged, and genuinely impressive. But Argus operates from aircraft at altitudes of around 20,000 feet. Taking that technology to space requires solving problems that don't have easy solutions. Orbital mechanics, radiation hardening, power requirements, thermal management in vacuum, data transmission bandwidth. The engineering challenges multiply exponentially. Does that mean it's impossible? No. The National Reconnaissance Office has orbited surveillance satellites with mirrors larger than Hubble's since the 1970s. Technology that seems impossible becomes operational when defense budgets and national security priorities align. The question isn't whether space-based gigapixel imaging could exist. The question is whether it would be aimed at comets. Spy satellites typically focus on Earth's surface, tracking military installations, monitoring nuclear facilities, capturing high-resolution imagery of strategic locations. Pointing those assets at deep space objects represents a different mission entirely, one that would fall under planetary defense rather than traditional intelligence gathering. Which brings us to Oracle 6. The Roman numeral 6 suggests this is at least the 6th iteration of whatever Oracle represents. That naming pattern matches known satellite constellations, where successive generations receive sequential numbers. Keyhole satellites, for instance, progressed through multiple versions as technology improved, but Oracle hasn't appeared in any declassified documents or leaked presentations from the Snowden archives. If it exists, it's more tightly held than most National Reconnaissance Office programs. The alternative interpretation is that Oracle refers to a processing system rather than a physical satellite. Intelligence agencies use code names for software platforms, algorithms, analytical frameworks. Oracle could be the system that processes sensor data from multiple sources, fusing imagery from different platforms into unified targeting solutions. That would explain why it appears in the file header alongside ARGUS-VIS. The sensor captures raw data. Oracle processes it into actionable intelligence. Then we have Cassandra, the umbrella designation that supposedly encompasses this entire planetary defense tracking network. In Greek mythology, Cassandra received the gift of prophecy, but was cursed so no one would believe her warnings. It's a darkly appropriate name for a system designed to detect cosmic threats. The 2005 proposal that used this name envisioned a network of ground-based telescopes specifically dedicated to tracking near-Earth objects. The proposal emphasized rapid detection and characterization of potentially hazardous asteroids and comets, providing early warning for planetary defense responses. That proposal never received congressional appropriation in public budget documents. Congressional funding for planetary defense goes to NASA's Planetary Defense Coordination Office, which coordinates with international partners using openly published observational data. If a classified parallel system exists, it would represent a significant duplication of effort unless it serves purposes beyond pure scientific observation. Here's where the analysis gets tricky. Real classified programs follow certain patterns. They use compartmented security protocols, limiting access to specific individuals with need-to-know clearance. They employ cover stories and misdirection to hide their true capabilities. They maintain operational security through air-gap networks that never touch the public internet. Getting data from such a system onto a public forum would require either a deliberate leak by someone with authorized access, or a security breach so severe it would trigger massive investigations. The metadata in leaked files can reveal authenticity or expose fakes. Real sensor data includes telemetry, timestamp information, calibration parameters, processing history. These details can be verified or disproven by people who understand how imaging systems actually work. The Cassandra files that surfaced on November 2nd reportedly lacked the kind of detailed metadata you'd expect from actual classified intelligence products. The image headers showed the designation strings, but not the technical parameters that would accompany legitimate sensor data. This absence cuts both ways. It could mean the files are fake, created by someone who understood designation conventions but didn't have access to real data. Or it could mean someone stripped the metadata deliberately before leaking, removing identifying information that could trace back to specific systems or operators. Compare this to how NASA and ESA release scientific imagery. When Hubble captures an image, the data comes with extensive documentation. Observation date and time, exposure settings, filter configurations, instrument specifications, processing algorithms applied, even the names of the scientists who scheduled the observation. Everything is transparent because reproducibility is fundamental to the scientific method. Other researchers need to verify results, need to reanalyze raw data using different techniques, need to build on previous observations. Classified intelligence products work exactly opposite. They hide sources and methods, protect capabilities from adversary analysis, restrict distribution to cleared personnel. If the Cassandra files were real, we wouldn't expect them to include the kind of transparent documentation that accompanies scientific data releases. The psychology of leaks also matters here. Ambiguity fuels conspiracy theories more effectively than clear evidence. If the Cassandra files had shown unambiguous alien spacecraft, the images would be easier to debunk as obvious hoaxes. If they'd shown nothing but a normal comet, no one would care. But by showing something ambiguous, something that could be interpreted multiple ways depending on your assumptions, the leak generates exactly the kind of endless debate that keeps conspiracy theories alive. Online communities tried to trace the leak's origin. The account that first posted the files was created hours before the upload, used anonymizing services to hide its location, and disappeared within a day. Other users claimed to have seen similar images months earlier on different forums. Some pointed to inconsistencies in image compression that suggested multiple generation copies rather than original files. Others insisted they could identify artifacts consistent with specific sensor types. None of these amateur investigations reached definitive conclusions. The chain of custody remained broken, the provenance unverifiable. Without the original files, without access to the sensor that allegedly captured them, without cooperation from the agencies that would operate such systems, authentication becomes impossible, which leaves us in an uncomfortable position. We can't prove the files are real. We can't prove they're fake. We're stuck in the realm of speculation, which is exactly where the most interesting questions start to emerge. Because if those images showed even a fraction of what they claim to show, then the physics of 3I Atlas becomes very strange indeed. How would the object's behavior contradict our understanding of comet mechanics? That's the question we need to explore next. Comets are supposed to be simple. Dirty snowballs, astronomers call them, chunks of ice and rock left over from the solar system's formation. When they approach the sun, solar radiation heats the surface, causing frozen volatiles to sublimate directly from solid to gas without passing through a liquid phase. This outgassing creates the coma, that fuzzy atmosphere that makes comets visible from Earth. Radiation pressure and solar wind push the gas and dust away from the sun, forming the characteristic tail that always points away from our star, regardless of the comet's direction of travel. This is textbook physics, observed in thousands of comets over centuries of astronomical study. We understand the process so well that we can predict cometary behavior with remarkable accuracy. We know how brightness should change as a comet approaches and recedes from the sun. We can model how tail length and density should vary with solar distance. We've even landed spacecraft on comets, drilled into their surfaces, analyzed their composition directly. 3I Atlas should follow these same rules. It's an icy body, confirmed by spectroscopic observations that detected water vapor, carbon dioxide, carbon monoxide, and other volatile compounds. When it approached within 24 million miles of the Sun on November 1st, 2025, temperatures at its surface would have exceeded 300 degrees Celsius. Any exposed ice should have vaporized rapidly, creating intense outgassing that would obscure the nucleus in a thick coma. NASA's observations confirmed exactly this expected behavior. Hubble imagery from late October and early November showed 3I Atlas developing a bright coma and prominent tail. The object brightened dramatically as solar heating increased sublimation rates. Spectroscopic analysis detected emission lines consistent with water, carbon dioxide, and diatomic carbon molecules. Everything looked normal for a comet making its first passage through the inner solar system. But the leaked Cassandra files told a different story. According to those images, 3I Atlas maintained a sharply defined geometry, even at perihelion. Instead of a fuzzy nucleus obscured by gas and dust, the alleged sensor data showed distinct structural features with angular edges and clear boundaries. The thermal profile reportedly displayed hotspots that didn't align with simple solar heating patterns. Most troubling, the plasma emissions showed directionality that standard sublimation physics doesn't explain. Let's unpack what that directional plasma claim actually means. Normal cometary outgassing occurs because surface ice heats unevenly. The side facing the sun receives direct radiation and heats faster, producing more intense jets of vapor. But these jets are fundamentally passive. They're driven by temperature gradients and vapor pressure, not by any active control mechanism. The gas expands outward in patterns determined by surface geography and rotation. Sometimes you get focused jets shooting from specific vents or fractures, but these still follow predictable physics based on thermal models. The Cassandra files allegedly showed something different: plasma streams that appeared to pulse with regularity, emissions that seemed coordinated rather than random, directional thrust that would require either impossible coincidences in surface features or something actively controlling the outgassing pattern. This is where we need to talk about non-gravitational acceleration, because it's a real phenomenon that complicates the analysis. When comets outgas asymmetrically, the escaping vapor exerts a tiny rocket force on the nucleus. This isn't speculation, it's measured fact. Astronomers have tracked orbital deviations in many comets caused by this rocket effect. The force is small, but over time it changes the comet's trajectory in ways that gravity alone can't explain. Non-gravitational acceleration is natural, well understood, and happens to comets all the time. It doesn't mean the comet is artificial. It means outgassing is uneven, which makes perfect sense, given that comet nuclei are irregularly shaped objects with varying composition across their surfaces. But here's where the leaked claims become harder to dismiss casually. If 3I Atlas really did show pulsed emissions with timing regularity, that would fall outside the normal range of non-gravitational effects. Natural outgassing can vary as a comet rotates, producing jets that appear and disappear as surface features turn into and out of sunlight. But truly periodic pulsing with precise timing would require an internal mechanism controlling the vapor release. Something clocks, something that maintains rhythm independent of random thermal variations. The European Space Agency's observations from late November added interesting complexity to this picture. Hubble re-observed 3I Atlas on November 30th, capturing detailed images of its coma and tail structure. The images showed multiple jets emanating from the nucleus, with brightness variations suggesting rotational modulation. This is completely normal for comets, but some researchers noted that the jet patterns seemed more organized than typical, with symmetries that could indicate either unusual surface features or, if you want to speculate, deliberate control. Spectroscopic data from James Webb and ALMA, the Atacama Large Millimeter Array, revealed another puzzle. The outgassing composition was dominated by carbon dioxide, with unusually high levels of methanol and hydrogen cyanide. This chemistry isn't impossible for comets, but it suggests formation in an extremely cold environment, colder than the outer regions of our own solar system. That makes sense for an interstellar visitor that spent billions of years in the space between stars. But it also means we're dealing with an object whose material properties might behave differently than solar system comets under thermal stress. Could these exotic ices produce outgassing patterns that mimic artificial propulsion? That's actually a legitimate scientific question. If the composition and structure differ significantly from known comets, our thermal models might not accurately predict how 3I Atlas responds to solar heating. Jets could form in unexpected configurations. Vapor could be released in bursts rather than continuously. Surface features could create optical illusions that look artificial in low-resolution imagery. The fringe speculation goes further, suggesting 3I Atlas might be a dormant probe, a von Neumann machine that spent eons drifting through interstellar space before encountering our solar system. Under this scenario, what we're interpreting as cometary outgassing could actually be a propulsion system activating, using solar energy to power ion drives or plasma thrusters that allow course corrections. The structured geometry would be a spacecraft hull rather than a rocky nucleus, designed to withstand extreme temperatures through advanced materials science. This is, to be absolutely clear, wild speculation without supporting evidence. Nothing in the verified observations requires artificial origins. The chemistry, the orbital mechanics, the observed brightness changes, all of this fits within natural explanations for an interstellar comet with unusual but not impossible composition. Yet the speculation persists because we've never studied an interstellar comet up close. We've observed exactly 2 confirmed interstellar objects before 3. I Atlas, Oumuamua in 2017, and Borisov in 2019. Oumuamua showed non-gravitational acceleration that sparked intense debate about its nature. Borisov looked like a normal comet, but was gone before we could study it extensively. 3I Atlas is only the 3rd data point in our understanding of objects from other star systems. With such a limited sample size, our assumptions about what's normal might be completely wrong. Maybe interstellar comets regularly show features we'd consider bizarre for solar system objects. Maybe the physics operating in the space between stars produces structures we don't have experience recognizing. Maybe we're anthropomorphizing natural phenomena, seeing patterns and purpose where none exists because our brains evolved to detect agency even in random events. Or maybe, just maybe, something traveled across light years of space and arrived in our solar system exactly when our technology reached the point where we could detect it. Before we chase that thought down the rabbit hole, we need to ask a more fundamental question. Do we even have the real source material? Are these leaked files legitimate intelligence products, or are we analyzing fiction? The first rule of intelligence analysis is verify your sources. The second rule is trust nothing without independent confirmation. When classified files appear on public forums with no attribution, no metadata, no chain of custody documenting their journey from secure server to internet upload, alarm bells should ring immediately. Chain of custody matters in any investigation, whether we're talking about criminal evidence, scientific data, or leaked intelligence documents. Without knowing where information came from, how it was handled, who had access to it, we can't assess its reliability. The Cassandra files failed this basic test spectacularly. They materialized on a forum known for conspiracy theories, posted by an anonymous account that vanished before anyone could ask questions, with no documentation explaining their origin or authenticity. This isn't how legitimate intelligence leaks happen. When Edward Snowden exposed NSA surveillance programs, he provided reporters with massive document caches that could be cross-referenced and verified. The documents included metadata showing creation dates, author information, classification markings that matched known government systems. Journalists could authenticate the materials before publication, could contact current and former intelligence officials to confirm the documents reflected real programs. The Cassandra files came with none of that supporting evidence. just the images themselves, the provocative file headers, and claims that couldn't be substantiated. History teaches us to be skeptical. The UFO research community has been burned repeatedly by hoaxes, misidentifications, and disinformation. Grainy photographs turn out to be weather balloons or conventional aircraft. Leaked documents prove to be fan fiction written by enthusiasts. Videos showing impossible maneuvers are revealed as digital effects or drone footage with misinterpreted scale. Some hoaxes are crude, obvious fakes that fall apart under minimal scrutiny. Others are sophisticated productions that fool even experienced researchers. The line between authentic mystery and crafted deception isn't always clear, especially when dealing with topics where the truth itself is classified and unavailable for comparison. Consider the metadata question. Digital files contain hidden information about their creation and modification history. Cameras embed EXIF data recording exposure settings, GPS coordinates, timestamps. Image editing software leaves traces in file headers showing which programs opened and modified the image. Compression algorithms introduce specific artifacts that reveal how many times a file has been saved and at what quality settings. Forensic analysis can extract all this information and use it to build a file's biography. When the Cassandra images circulated on Reddit and specialized forums, several researchers with image forensics experience attempted to analyze the metadata. Their findings were inconclusive, which is itself suspicious. Real sensor data should contain rich metadata, documenting every step from photon capture to final image file. Stripped metadata suggests deliberate scrubbing, but it also prevents authentication. Some analysts pointed to compression artifacts that suggested multiple generation copies. When you repeatedly save and compress an image, quality degrades in characteristic ways. If the Cassandra files showed signs of multiple compression cycles, that would indicate these weren't original sensor outputs, but rather copies of copies, each generation introducing more noise and losing more detail. Original intelligence imagery would be distributed in lossless formats or high-quality compressed files with full metadata intact. Other researchers noted inconsistencies in the alleged file header formatting. Classification markings follow strict protocols in real government systems. The precise placement of labels, the specific abbreviations used, the formatting of security caveat, all of these details are standardized to prevent confusion and maintain operational security. People who work with classified material every day recognize when markings look wrong, when the bureaucratic boilerplate doesn't match established patterns. Several former intelligence analysts commenting in online threads pointed out that Cassandra/Oracle 6 vertical bar ARGUS-VIS doesn't quite match how real compartmented programs would be labeled. The syntax feels close, but not exact, like someone copied the style without understanding the underlying rules. Real classification markings include specific distribution controls, date-time groups, originating agency identifiers. The leaked headers showed none of these supporting details. The community reaction split. Predictably, true believers insisted the files were authentic, explaining away inconsistencies as necessary operational security measures taken during the leak process. Skeptics argued the entire thing was a hoax, pointing to the convenient lack of verifiable details as evidence of fabrication. The middle ground acknowledged the images were interesting, but remained agnostic about their origin given the absence of conclusive proof either way. This ambiguity is actually valuable to anyone running a disinformation campaign. If your goal is to muddy the waters around a real classified program, you leak plausible but unverifiable information that generates endless debate without revealing actual capabilities. If your goal is to hoax people for attention or social manipulation, you create content ambiguous enough that believers and skeptics can argue forever without reaching resolution. Real NASA and ESA data releases operate in exactly the opposite manner. When a scientific observatory captures images, The raw data becomes available through public archives within months. Researchers worldwide can download the same files, process them using their own algorithms, verify that published results match the actual observations. This transparency is fundamental to the scientific method. Claims without reproducible data aren't science, they're storytelling. The James Webb Space Telescope raw data sits on servers accessible to anyone with internet access. You can download the exact photons that JWST's detectors captured, apply your own calibrations, generate your own images. If you find something in the data that official releases didn't mention, you can publish your analysis and other researchers can check your work. This open system makes fraud nearly impossible and mistakes easy to catch. Classified intelligence operates with opposite priorities. Hiding sources and methods takes precedence over transparency. If ARGUS-VIS really exists as a classified sensor system, we wouldn't expect its raw data to be publicly downloadable. We wouldn't get detailed documentation of its capabilities. We'd get carefully filtered information released only when disclosure serves strategic purposes. This creates an asymmetry that conspiracy theories exploit. Science must prove itself through transparency and reproducibility. Intelligence can hide behind classification and neither confirm nor deny claims about secret programs. The absence of evidence isn't evidence of absence when dealing with classified capabilities. Just because we can't verify something doesn't mean it doesn't exist. Psychology adds another layer. Human brains are pattern recognition machines optimized to detect threats and identify agency. We see faces in clouds, hear voices in random noise, find conspiracies in coincidence. When presented with ambiguous information about potential threats from space, our neural architecture predisposes us toward believing the exciting, frightening possibility rather than the mundane explanation. The Cassandra files pushed all these psychological buttons perfectly. Classified government systems, interstellar visitors, geometry that might be artificial, plasma emissions that could be propulsion. Each element adds credibility to the others in a feedback loop where believers cite one piece of ambiguous evidence to support another equally ambiguous claim. Breaking this loop requires returning to fundamentals. What can we actually verify? What do the unambiguous observations tell us? Setting aside the leaked files entirely, what does legitimate scientific data reveal about 3I Atlas? Those are the questions we need to answer before we can evaluate whether the Cassandra files showed us something real or something fabricated. But first, let's entertain the wildest possibilities. What if 3I Atlas isn't a comet at all? What if we're looking at something that challenges every assumption about our place in the universe? Official science is clear. 3I Atlas is a comet, an interstellar comet with unusual chemistry and interesting behavior, but still fundamentally a natural object governed by physics we understand. Spectroscopic observations detected water, carbon dioxide, carbon monoxide, methanol, hydrogen cyanide, all molecules we'd expect from volatile ices formed in cold environments. The brightness variations match thermal models for a rotating nucleus with active sublimation. The orbital mechanics show an unbound hyperbolic trajectory consistent with an object that originated outside our solar system and will eventually leave it again. Everything fits within natural explanations. But let's play with the alternatives. Let's explore the scenarios that exist at the fringes of plausibility, the ideas that serious scientists mostly dismiss but can't entirely disprove, the what-if questions that make space so simultaneously terrifying and exhilarating. Hypothesis 1. 3I Atlas is a dormant probe sent by an extraterrestrial civilization. Under this scenario, what appears to be a comet is actually a spacecraft covered in ice accumulated during billions of years, traveling through interstellar space. The volatile coating protects the probe's mechanisms from micrometeorite impacts and radiation exposure. When it enters a solar system, Solar heating sublimates the ice layer, revealing the artificial structure underneath, while also providing energy for systems to reactivate. This isn't purely science fiction. Scientists have seriously proposed that interstellar probes might deliberately disguise themselves as natural objects to avoid detection by less advanced civilizations. If you wanted to study a star system without announcing your presence, mimicking a comet would be an effective strategy. You'd enter the system on a natural-looking trajectory, gather observations during your passage, then depart before anyone realized you were anything but ice and rock. The challenging part is explaining why such a probe would reveal itself by behaving anomalously. If stealth was the goal, why show geometric structures or directed plasma emissions that might trigger suspicion? The counter-argument suggests the probe might not care about stealth after observing the target civilization's technology level. Once it determines we're capable of detecting but not intercepting it, there's no operational reason to maintain camouflage. Hypothesis 2. 3I Atlas is a relic from an ancient advanced civilization, perhaps one that died out millions or billions of years ago. This scenario imagines long-dead aliens who once colonized the galaxy, leaving behind artifacts that still orbit through space long after their creators vanished. These relics might be automated systems that no longer function as designed, or they might be time capsules deliberately launched to carry information forward into deep time. The appeal of this idea is that it explains why we see only one object rather than many. A thriving galactic civilization would presumably send numerous probes, but the remnants of an extinct species might be incredibly rare, scattered across interstellar distances with only occasional items drifting through inhabited systems. Of course, this hypothesis faces the same evidential problems as the active probe scenario. We have no confirmed examples of alien technology to compare against. We don't know what artificial materials would look like after billions of years in space. We can't distinguish between exotic natural materials formed in other star systems and manufactured substances created by non-human engineering. Hypothesis 3. 3I Atlas represents exotic physics objects that our current models don't adequately describe. This is the most scientifically respectable of the fringe ideas because it doesn't invoke aliens, just gaps in our understanding of possible material states and formation processes. Interstellar space is cold, radiation-bathed, and nearly empty. Objects forming in such environments might develop structures we've never observed in solar system comets. Crystalline ices could form in configurations impossible under higher pressure conditions. Organic molecules might polymerize in ways that create rigid frameworks rather than loose aggregates. Magnetic fields could organize metallic dust into geometric patterns during the accretion process. The chemistry detected in 3I Atlas supports this possibility. The high methanol and hydrogen cyanide content suggests formation in environments with different elemental abundances and temperature histories than our solar system experienced. If the building blocks were different, the final object might have properties we don't anticipate. Amateur astrophotographers captured stunning images of 3I Atlas showing a distinctly greenish coma, likely from cyanogen and diatomic carbon emissions. These colors aren't unprecedented in comets, but their intensity in an interstellar visitor hints at chemistry running hot in ways our models might not capture fully. Chemical reactions that would be slow or impossible in solar system comets might proceed rapidly when exotic ices sublime under solar heating. Now, we need to acknowledge what we're doing here. These hypotheses are intellectual exercises, thought experiments that help us understand what kinds of observations would actually be required to support extraordinary claims. None of them are verified or even strongly supported by current data. They're the narratives that fill the gap between what we can observe and what we can imagine. Harvard astrophysicist Avi Loeb has become perhaps the most visible scientific voice willing to publicly discuss non-standard interpretations of interstellar objects. His comments about Oumuamua's non-gravitational acceleration sparked fierce debate in the astronomical community. Loeb suggested that if we can't adequately explain the acceleration with natural outgassing, we should consider technological explanations. His arguments are more nuanced than media coverage sometimes suggests, but he's definitely pushed for taking the possibility of artificial origins more seriously than most scientists find comfortable. The mainstream response has been that extraordinary claims require extraordinary evidence, and we simply don't have that evidence. Non-gravitational acceleration can be explained by asymmetric outgassing, even if we can't model it perfectly. Unusual geometry could result from irregular nucleus shapes and rotation. Exotic chemistry is interesting, but doesn't require artificial origins. This conservative stance is scientifically sound. We shouldn't invoke aliens to explain phenomena that natural processes can account for. Occam's razor suggests we prefer simpler explanations over more complex ones when both fit the available data. A comet with unusual properties is vastly simpler than an alien probe, but the conservative stance also acknowledges its limitations. We've observed exactly 3 confirmed interstellar objects ever. That's an absurdly small sample size to base confident conclusions on. The diversity of planetary systems we've discovered suggests formation conditions vary enormously. We know solar system comets show tremendous variation in composition, structure, and behavior. Interstellar objects formed in completely different environments might show even greater diversity. We're essentially trying to understand an entire category of astronomical phenomena based on 3 examples. That's like trying to understand Earth biology by examining 3 organisms. You might get lucky and pick representative samples. You might pick 3 bacteria and completely miss the existence of animals, plants, and fungi. You might pick a whale, an oak tree, and a jellyfish, and come away thinking life has no unifying principles at all. The truth is, we need more data. We need to observe dozens or hundreds of interstellar objects, study their compositions and behaviors in detail, build statistical models of their properties. We need missions that can rendezvous with these visitors while they're still in our solar system, spacecraft that can capture close-up imagery and sample their surfaces directly. Several such missions have been proposed. The European Space Agency studied concepts for fast response spacecraft that could launch on short notice when new interstellar objects are detected. NASA's Jet Propulsion Laboratory designed mission profiles using ion propulsion and gravity assists to reach high velocities needed to catch objects on hyperbolic trajectories. None of these missions have received funding yet because the technical challenges are substantial and the wait time between target opportunities is long. So for now, we're limited to remote observations, watching these cosmic messengers briefly as they pass through our neighborhood and then vanish back into the void. Every observation adds to our understanding, but the picture remains frustratingly incomplete. Which brings us back to 3I Atlas and the Cassandra files. Even if the leaked images turn out to be hoaxes, even if every anomalous claim proves to be misinterpretation or fabrication, the real object still deserves our attention. Because real or imagined, classified, or public, what 3I Atlas represents is a window into interstellar space, a sample of matter that spent billions of years outside our solar system and now briefly visits our cosmic neighborhood. What are scientists actually observing right now? What does the unambiguous data tell us about this interstellar traveler? While internet forums debated leaked files and speculated about alien probes, professional astronomers were busy doing what they do best, pointing telescopes at interesting objects and collecting data that will be analyzed for years to come. The Hubble Space Telescope re-observed 3I Atlas on November 30th, 2025, nearly a month after perihelion. The images showed a well-developed coma extending thousands of miles from the nucleus, with a prominent tail streaming anti-sunward. Multiple jets were visible emanating from the central condensation, suggesting active vents distributed across the nucleus surface. The brightness had decreased from its perihelion peak, but remained well above pre-approach levels, indicating sustained outgassing despite the object moving away from the Sun. These observations are invaluable because Hubble's cameras are meticulously calibrated. We know exactly how sensitive they are, what wavelengths they detect, how to convert measured photon counts into physical properties like brightness, color, and size. The data isn't ambiguous or subject to interpretation about sensor capabilities. It's quantified, reproducible, and available for independent analysis. MAVEN, the Mars Atmosphere and Volatile Evolution spacecraft orbiting the Red Planet, captured its own observations of 3I Atlas. From Mars's perspective, the geometry was different than Earth-based views, allowing scientists to construct three-dimensional models of the coma structure. The Mars Reconnaissance Orbiter added high-resolution imaging with different filters, revealing gas halos that extended even further than visible light observations suggested. Having multiple vantage points transforms two-dimensional images into spatial understanding. When you observe from Earth, you see one projection of the object. When Mars-based spacecraft observe from a different angle, you can triangulate, can measure actual distances and structures rather than just apparent sizes. This stereoscopic effect reveals whether features are real, physical structures, or optical illusions caused by viewing geometry. Amateur astronomers made crucial contributions too. Backyard telescopes scattered across the globe provided time coverage that professional observatories couldn't match. While Hubble can only observe 3I Atlas for a few orbits due to scheduling constraints, amateurs tracked the object night after night, documenting rapid brightness variations that hinted at rotation periods and outburst events. Some of these amateur images are stunning. High-quality astrophotography has advanced enormously in recent years, thanks to affordable digital cameras, computerized tracking mounts, and image processing software. The greenish coma visible in many images results from cyanogen and diatomic carbon emissions, molecules that fluoresce at specific wavelengths when energized by solar ultraviolet radiation. The color isn't paint or artifice, it's quantum mechanics. Electrons transitioning between energy states and emitting photons in the process. The European Space Agency coordinated observations with multiple spacecraft as well. Jupiter Icy Moons Explorer, currently on its way to Jupiter, pointed its instruments toward 3I Atlas during a brief window when the geometry was favorable. Lucy, NASA's mission to study Trojan asteroids, contributed observations from its position in the inner solar system. Even spacecraft not designed for comet studies provided valuable data points. This international coordination demonstrates modern astronomy at its best. Dozens of facilities sharing data, publishing results openly, building collective understanding through transparent collaboration. If classified sensors really were observing 3I Atlas in parallel, that information exists in a completely separate domain, analyzed by different people using different methodologies for different purposes. The spectroscopic observations deserve special attention because they reveal composition in ways imaging cannot. When molecules are excited by solar radiation, they emit light at characteristic wavelengths determined by their quantum structure. By spreading that light into a spectrum and measuring intensity at different wavelengths, we can identify which molecules are present and estimate their abundances. James Webb. Space Telescope's infrared spectrographs detected multiple emission features consistent with water, carbon dioxide, carbon monoxide, methanol, and formaldehyde. The relative abundances were unusual, with much more carbon dioxide and less water than typical solar system comets. This composition suggests formation in a very cold environment where carbon dioxide could condense as ice, colder than the outer regions of our solar nebula. ALMA, the Atacama Large Millimeter Array in Chile, observed at even longer wavelengths, detecting millimeter wave emissions from complex organic molecules. The hydrogen cyanide detection was particularly interesting because this molecule is a precursor to amino acids under the right chemical conditions. Interstellar comets delivering complex organic chemistry to young planetary systems could have played a role in the origin of life across the galaxy. Polarimetric studies added another dimension to the observations. When light scatters off dust grains, it becomes polarized, with the electric field oscillating in a preferential direction. The degree and orientation of polarization depends on grain size, shape, and composition. By measuring polarization at different wavelengths, scientists can characterize the dust particles in the coma without needing to sample them directly. The polarimetry results for 3I Atlas showed light scattering consistent with submicron-sized grains composed of silicate and carbon compounds. Nothing unusual there. These are the typical dust components in comets. But some measurements hinted at unexpected wavelength dependence that could indicate unusual grain shapes or exotic materials mixed with the typical components. Artificial intelligence is playing an increasing role in analyzing this flood of data. Machine learning algorithms trained on thousands of comet observations can automatically identify features, track changes over time, distinguish real structures from instrumental artifacts. These AI systems don't replace human expertise, but they augment it, processing vast datasets faster than traditional methods allow. One interesting application involves searching for fine-scale structures in coma images. Jets, shells, disconnection events, all of these features carry information about nucleus activity and rotation. AI can scan through time series imagery, flagging potential events for human review. In the case of 3I Atlas, automated systems identified brightness variations consistent with rotation periods between 8 and 12 hours, though the exact value remains uncertain due to complex light curve shapes. The technology enabling these observations continues to improve. The extremely large telescope under construction in Chile will have a primary mirror 39 meters in diameter, dwarfing current telescopes. With its massive light-gathering power and adaptive optics correcting for atmospheric distortion, ELT will resolve details in comet nuclei that currently appear as single pixels. NASA's Nancy Grace Roman Space Telescope, scheduled to launch in the late 2020s, will survey huge swaths of sky with sensitivity that will detect fainter interstellar objects earlier in their approach. But technology cuts both ways. The proliferation of satellite constellations, particularly mega constellations with thousands of satellites in low Earth orbit, threatens ground-based astronomy. Bright satellites crossing fields of view create streaks in long exposure images, contaminating data and reducing scientific productivity. Astronomers are working with satellite operators to mitigate these impacts, but the problem is growing faster than solutions can be implemented. Ironically, these same satellite networks enable global internet coverage and provide the communication infrastructure that allows real-time coordination of astronomical observations. We're building a technological civilization that's simultaneously making space more accessible and more polluted, enhancing our ability to study the universe while degrading the environment from which we observe it. 3I Atlas observations will continue for months as the object recedes from the sun. Brightness will fade as sublimation rates decrease with distance, eventually becoming too dim for all but the largest telescopes to detect. Before it disappears entirely, astronomers hope to refine measurements of its nucleus size, rotation period, composition, and trajectory. Each additional observation constrains models and reduces uncertainties. The data gathered from this one object will inform our understanding of interstellar space, comet formation, the diversity of planetary systems, and the transport of organic molecules between stars. This is science operating as it should, building knowledge through careful observation and rigorous analysis. But this is also where the Cassandra files controversy reveals something important about how we process information in an age of information overload. We have access to unprecedented amounts of data, but we also face unprecedented amounts of noise, misinformation, and deliberate deception. Separating signal from noise requires critical thinking skills that aren't universally distributed. The broader story of 3I Atlas extends beyond one comet or one leaked file. it's part of the larger project of understanding our cosmic context, of figuring out where we fit in a universe that keeps revealing itself to be stranger and more complex than we imagined. What does the cutting edge of astrophysics tell us about that bigger picture? The universe refuses to hold still long enough for us to understand it completely. Every time we think we've figured out the rules, new observations reveal phenomena we didn't anticipate. This is simultaneously frustrating and exhilarating, the perpetual state of science operating at the boundaries of knowledge. Recent breakthroughs in understanding galaxy evolution illustrate this perfectly. We've known for decades that most large galaxies host supermassive black holes at their centers. What we didn't understand was the connection between galaxy mergers and black hole activation. New observations from the James Webb Space Telescope have revealed that when galaxies collide and merge, their central black holes can be triggered into active feeding states, transforming quiet galaxies into brilliant quasars. This matters for understanding cosmic history because galaxy mergers were much more common in the early universe when galaxies were closer together. The rate of black hole activity we observe at different epochs tells us about the assembly history of galactic structures over cosmic time. It's a puzzle where 3I Atlas-like objects play a tiny but interesting role because interstellar comets and other small bodies get gravitationally redistributed during galaxy mergers, potentially carrying organic molecules and volatile compounds between star systems on galactic scales. The delivery of organic chemistry via comets and asteroids is no longer a fringe idea. We've detected amino acids in meteorites that fell to Earth. We've observed complex organic molecules in interstellar clouds. We've measured prebiotic chemistry in comet samples returned by space missions. The ingredients for life appear to be distributed widely throughout the galaxy, transported by exactly the kind of icy bodies that 3I Atlas represents. The methanol and hydrogen cyanide detected in 3I Atlas aren't just interesting chemistry, they're building blocks. Hydrogen cyanide can polymerize into adenine, one of the nucleotide bases in DNA. Methanol participates in chemical pathways that produce formaldehyde and more complex organic molecules. Under the right conditions, with liquid water and energy sources, this chemistry could bootstrap toward life. We don't know if life originated on Earth or arrived from space. The leading hypothesis involves chemical evolution in terrestrial environments. Warm little ponds or hydrothermal vents where organic molecules could concentrate and react. But comets delivering organic feedstock would have accelerated that process enormously, providing raw materials that didn't need to be synthesized from simpler precursors. If this delivery mechanism operates throughout the galaxy, then every star system receives gifts of complex organic chemistry from interstellar space. Some of those deliveries hit planets in habitable zones, where liquid water and stable temperatures allow chemistry to explore all possible reaction pathways. Some of those chemical experiments discover self-replication, metabolism, evolution. Some of those evolutionary processes produce intelligence, technology, civilizations that eventually look out at the stars and wonder if they're alone. This is the most profound implication of studying interstellar objects. They're messengers from other star systems, samples of matter that formed in alien environments. And now visit our neighborhood. Each one teaches us about conditions elsewhere in the galaxy, about the diversity of planetary systems, and the range of possible chemistries and structures that exist beyond our direct experience. Only 3 confirmed interstellar visitors. Oumuamua with its puzzling acceleration and unusual light curve. Borisov looking reassuringly comet-like, but gone before we could study it properly. 3I Atlas with its extreme chemistry, and, if we believe unverified leaks, possibly strange geometry and emissions. That's an absurdly small sample to generalize from. Statistical models suggest we should detect several interstellar objects per year with current survey capabilities. The fact that we've only confirmed 3 means either they're rarer than models predict, or they're harder to identify than we assume, or we're simply not looking carefully enough. Future surveys with faster cadence and better coverage will answer this question by finding more objects or constraining their absence. The Vera C. Rubin Observatory, beginning operations in the mid-2020s, will revolutionize time domain astronomy. Its telescope will image the entire visible sky every few nights, detecting anything that moves, changes brightness, or appears newly. Interstellar objects will announce themselves through their motion against the background stars, and automated software will flag them for follow-up within hours of detection. This early detection is crucial because it enables mission planning. If we discover an interstellar visitor while it's still beyond Jupiter's orbit, we have time to design, build, and launch an intercept mission that could rendezvous with the object and study it up close. Currently, we discover these objects during or after their closest approach to the Sun, too late to reach them with existing spacecraft. Imagine what we could learn from a dedicated mission to an interstellar object. Imaging the nucleus at meter-scale resolution, landing instruments to measure composition directly, drilling into the surface to examine layered structure, deploying penetrators to study the interior, returning samples to Earth for laboratory analysis. All of this is technically feasible with existing technology if we can detect the objects early enough and commit resources to the mission. The scientific return would be immense. We'd learn about planet formation in other stellar systems. We'd constrain models of how planetary systems evolve and inject material into interstellar space. We'd discover what chemistry prevails in environments with different elemental abundances. We'd test whether organic molecules survive interstellar transit. We'd measure radiation damage and space weathering effects on timescales of millions of years. And yes, we'd definitively determine whether any artificial structures or materials are present. If 3i Atlas really were an alien probe, a close-up mission would reveal that immediately. No more ambiguity, no more speculation, just unambiguous data about what the object actually is. That mission hasn't been funded yet. Budget priorities favor other objectives, and the wait time between interstellar object discoveries makes planning difficult. But the technical feasibility exists, and the scientific community continues advocating for such missions because the questions they could answer are genuinely important for understanding our cosmic context. Meanwhile, other branches of astrophysics push forward with transformative observations. The Event Horizon Telescope collaboration is imaging supermassive black holes at multiple wavelengths, testing general relativity in the strongest gravitational fields accessible to observation. Gravitational wave detectors are recording collisions of black holes and neutron stars across cosmic distances, providing completely new ways to study extreme physics. Exoplanet surveys have found thousands of worlds orbiting other stars, revealing planetary system diversity that challenges our assumptions about what's normal or typical. All of these advances contribute to the larger project of understanding where we are and what exists beyond our immediate experience. 3i Atlas is one small piece of that larger puzzle, but it's an important piece because it connects directly to the question of whether we're alone. Even if the Cassandra leak turns out to be a hoax, even if every anomalous claim gets explained away by natural processes, the real story of 3i Atlas still matters. This object traveled for potentially millions or billions of years through interstellar space before encountering our solar system. It carries information about other stellar environments encoded in its composition and structure. It demonstrates that matter regularly moves between star systems, that the galaxy is more interconnected than we might naively assume. Whether it's a comet or something more mysterious, whether classified sensors tracked it or the Cassandra files were elaborate fiction, 3i Atlas forces us to confront our ignorance about what's normal in the broader galaxy. We've spent centuries studying our own solar system, building models and theories based on 8 planets, a few dwarf planets, countless asteroids and comets. Then we discover that planetary systems show enormous diversity, that most stars host worlds completely unlike anything in our cosmic neighborhood. Interstellar objects are samples from that broader population, representatives of the immense variety that exists beyond our direct observation. Each one teaches us humility, reminds us that our experience is limited, pushes us to expand our understanding of what's possible. The real frontier isn't whether aliens exist or whether classified programs track interstellar visitors. The real frontier is understanding the universe as it actually is, with all its genuine strangeness and complexity, without needing to embellish or manufacture mystery. Because the truth is already stranger than any fiction we could invent. 3i Atlas will fade from view eventually, becoming too distant and dim for even our best telescopes to track. It will continue its journey back into interstellar space, carrying whatever secrets it holds into the void between stars. We may never know if it was just a comet with unusual chemistry or something more enigmatic, but we'll remember it as a reminder that the universe regularly delivers surprises, that our knowledge remains incomplete, and that the next interstellar visitor might arrive at any time, bringing new mysteries to explore and new questions to answer.